Hi everybody, let's look at this one from 1981. It's an AP Physics C question, so even though it doesn't have calculus, it's a pretty difficult question. It gets some wonky mathematics here. Anyway, let's check it out. So we got a swing seat of mass m is connected to a fixed point P by a massless cord of length L, and a child also of mass m, so we got mass m and mass m, sits on the seat and begins to swing with zero velocity to begin with at a position at which the cord makes a 60-degree angle with the vertical as shown in figure 1. So the child continues to swing down until the cord is exactly vertical, at which time the child jumps off in a horizontal direction. The swing continues in the same direction until the cord makes a 45-degree angle with the vertical as shown in figure 2. At that point, it begins to swing in the reverse direction, although they don't ask any questions about that swinging backwards the other way. So first up here is we are going to, they ask us to determine the speed of the child and seat just at the lowest position prior to the child's dismount. So this is a conservation of energy problem as the child and seat swing down to that lowest position there. Okay, so let's start off with this. The energy initial is equal to the energy final. In the beginning, we only had gravitational potential energy when they were up high and kinetic energy in the end when they were down low. Let's substitute in for each of these. We get mass times gravity times height is equal to 1/2 times mass times velocity squared. Then the masses cancel out, by the way. Let's solve for velocity. We get the square root of 2 times g times h when we do the algebra. And I'm like, oh, we did it. Except the thing is, h cannot be in there. It is not one of the acceptable parameters that we have. So let's draw this picture here and try and picture what we got to plug in here. So let's say this is the cord of length L, and then it's going to roughly swing down to here. And let's say that this is also length L right here. Well, we didn't start at L high. That would be true if we started all the way 90 degrees and swung down, but we didn't. And so how high are we? We are this high right here. So we are looking for that height. What is that height right there? Well, to get that, we've actually got to do one other side step here. We know that this height is the overall L minus this height. So what's this height right here? Well, this angle is 60 degrees. And this, see this little triangle right here? This is the adjacent side to that angle. So we can say that that distance right there is L cosine of 60 degrees. And they made it easy on us in this sense here because cosine of 60 is 1/2. So this is 1/2 L, which means that technically to get this side right here, we would have to take L minus L cosine of the angle, but this is just going to be L minus 1/2 L in this case, and so we just wind up with 1/2 L. And so our height right here is half of the length of the string there. So now we've got to plug it into here. So we get velocity is equal to the square root of 2 times g. Our height is 1/2 L. All right, let's clean that up. That looks a little messy. So our velocity is equal to the square root. This 2 will cancel that half, g L. Nice and simple there. All right, let's move on to part B. Part B is basically the same as part A, so I'm going to go through it very quickly here. All we're going to do, again, is conservation of energy. This time the swing swings up to here. We know we lost some energy, by the way, because we only go to 45 degrees, which means we're not as high, which means we lost some of our energy. All right, so in that one, let's think about it like this. We're going to do another conservation of energy. This time, we are starting with kinetic energy as the swing swings up to a certain height. So let's plug in for these. We got 1/2 times mass times velocity squared is mass times gravity times height. Masses cancel out. And again, the velocity needed to get up to a certain height, let's solve for that, is the velocity is equal to the square root of 2gh, just like we had before. But just like we had before, we're going to have to figure out what this height is. And so let's draw it again. Let's say that this right here is our length L right here. And then it's going to swing up to this height right here. And so this angle this time is 45 degrees. So all of that is L. We need to find what is this height we got to right here. And so again, we need to then find this side right here. And so this side right here is going to be L cosine of 45. And cosine of 45 just turns out to be 1 over the square root of 2. So this side right here winds up being L over the square root of 2, which means that this side, what I've got labeled as blue here, L, this is going to be the whole length L minus this, so this will be L minus L over the square root of 2 is our height. So now we can plug that into our equation here, and we get the velocity is equal to the square root of 2 times g, and our height is L minus L over the square root of 2, like that. You can just leave it like that. I'm going to clean it up one little bit here, and I'm going to factor out that g there, so we get 2gl, and we're left with 1 minus 1 over the square root of 2. Don't tell your math teacher that you got a square root on the bottom of a fraction there. Okay, so there we go. That's it. Nice, simple little answer there is our initial velocity to get to a height of 45 degrees. So now we're going to get some conservation of momentum here. It says determine the speed of the child immediately after he dismounts from the swing. So here's the thing. The child jumps off here. He takes away, in a sense, velocity from the swing because it doesn't get as high as it started over here. That must mean that he gained velocity. And how are we going to figure that out? Through the conservation of momentum. So we're going to look at it like this. The momentum of the system before he jumps off is equal to the momentum of the system after he jumps off. And so we can solve for this by thinking like, well, right at the bottom, that is the beginning of this problem, is at the bottom of the swing. So the momentum of the child swing seat system is equal to the momentum of the child afterwards plus the momentum of the seat afterwards. So as they are coming down here, this is going to be the mass of the child's seat system times its velocity. We know that they have a mass of 2m because this is both objects together, and we already solved for their velocity at the bottom. It's the square root of gl. So what's the momentum of the child afterwards? That's a mass of m, and then it's just the child, and then the velocity of the child afterwards, which is what we're looking for, and then the momentum of the swing is the mass of the swing, which is just m, times its velocity afterwards, which we solved for was 2gl times the quantity 1 minus 1 over the square root of 2. All right, oh man, this looks messy, but hey, at least this happens. The masses cancel out, and so we don't have to worry about that anymore. And look, actually, it's not so bad here, because when we go to look for this, all we got to do here is what we're trying to solve, just subtract this to the other side. And so let me use a different color. So we get the velocity of the child is equal to 2 times the square root of gl from here, minus all of this, the square root of 2gl, times the quantity 1 minus 1 over the square root of 2. And you can just leave it like that if you want, but I can't help it. I've got to clean this up a little bit. So let's put a little prime there, by the way, for afterwards, that we do something here. Let us write it like this. So this is going to be 2 square root of gl. I'm not going to mess with that. But here, what I'm going to do is write it in this fashion. Let's do this. You know what? I can see here I got a 2 here, or square root of gl here, and a square root of gl here. So let me factor out that square root of gl and do this. I got square root of gl. I'm going to factor that out, and that leaves me from here 2. And then I factored out the square root of gl here, so I get a minus a square root of 2 minus, and let me distribute this 2 here actually. So let's see here. I don't know. Maybe I made it worse. I made it worse. Don't do any of this. Just go with that right there. All right.